So earlier we learned about Darcy's law, which governs saturated water flow through soils and other porous media, but we learned about it in the context of a uniform soil. In the real world, often soil is not uniform. There's often layers, and so the purpose of this video is to show you the derivation of Darcy's law for layered soils. And this is a really convenient form and a convenient way to use Darcy's law for some real-world problems. Over here on the left, we have a hypothetical soil column. It consists of two layers, layer 1 on the top and layer 2 down below. And there's some water ponded on top of the column, as you can see, and there's water flowing through the soil column and collecting in a reservoir down beneath. And if we were measuring the rate of change of water in that reservoir, we could be measuring the soil water flux here, and you might want to know the flux through the top layer of the soil, which is given by Darcy's law for the top layer of the soil, where Q is the soil water flux, Q1 here for the first layer, which is the volume per unit area per unit time. And that is equal to, by Darcy's law for the first layer, the hydraulic conductivity of the first layer multiplied by the hydraulic gradient, which we'll write as delta, which means a change in H, which is the hydraulic head across layer 1. So delta H1 divided by the length or the thickness of the first layer. So that's Darcy's law for the first layer. Likewise, we could write Darcy's law for the second layer down here, and we'll say Q2, the flux through the second layer, is equal to the hydraulic conductivity of the second layer, K2, multiplied by the hydraulic gradient across the second layer. So delta H2, that's a change in hydraulic head across the layer, divided by the length of the second layer. Now here we're speaking in terms of hydraulic head. This is the same as the soil water potential, the total potential. And when it's in head units or length units, we can use the symbol capital H. Okay, now the other thing we know, if water is flowing through this column through both layers 1 and 2, and the system is at steady state, so it's not changing its water storage over time, then the flux through layer 1 has to be equal to the flux through the second layer, Q2, which is just equal to the total flux through the column, which we'll just call Q without any subscript. So to get Darcy's law in a convenient form for layered soils, we'll need to do some algebra. And the first thing that we want to do is to find out what is the hydraulic head at this point B, this interface between the two soils. And to do that, we can expand on the expression for the flux here at the first layer. We can say that the flux through the first layer is the conductivity of the first layer multiplying HA, which is the hydraulic head at point A, minus HB over L1. So if we start to rearrange this equation for our head at B, we'll rearrange. We'll move over the K1 and the L1 to the left-hand side. So we'll get Q1 times L1 over K1. And then let's subtract off the HA from the left-hand side and the right-hand side also. So we'll get minus HA equals minus HB. All right, or we can sort of change the signs here, and we can make this plus HB. All right, I'll just take a second here and erase that. And this will be a plus HA, and this will become a minus. So just changing the signs. So now we have an expression for HB. And we want to go down here into the second layer. We can expand this second layer expression to say K2 is HB minus HC divided by L2, right? The flux through the second layer is determined by the hydraulic head difference between points B and C and the length of that layer 2. But now we have a new expression for HB that we can plug in. Okay, so we're going to plug in that expression for HB that we had above. So then Q2 is equal to K2 over L2 multiplying this HA minus Q1 over L1 or times L1 over K1. That's just the expression I just found above, and all of that minus HC. Okay, so I just plugged that in. But now it's strange because I have these Q2 and Q1 in the same equation, but I'm going to use this fact that these things are just equal to Q, the flux through the column. So we have Q equals K2 L2 HA minus Q L1 K1 minus HC. Okay, so just starting to simplify this equation a little bit now. So you can see what I'm going to have to do to go any further is to bring over the K2 and the L2 to the other side. So that's what I'm going to do. I just grab my eraser here again, make a little space for us. Alright, so now just sort of rearranging from here, we can work up the other way. You can see that Q times L2 over K2, and then we can subtract over this, or add this term to both sides, Q L1 K1, and that just leaves us on the right hand side with HA minus HC. So it's starting to look a bit more simple. And then we can factor out the Q. So we just get Q multiplying L2 over K2 plus L1 over K1 equals HA minus HC. All right, any more simple still. And now we're just going to divide. Now we'll go back down the other way here and get to our final result. So if we divide, then we get Q equals HA minus HC L2 over K2 plus L1 over K1. So that's Darcy's law for layered soils. Now we can write this in a bit more simplified term if we introduce simplified way if we introduce the hydraulic resistance. So we're going to let this L over K, so the length of the soil layer, thickness of a soil layer divided by its hydraulic conductivity equal what we'll call the hydraulic resistance. And we'll use the symbol RH, hydraulic resistance. So if we do that notation, then we can write Darcy's law for layered soils in terms of hydraulic resistance. And we'll get Q, the flux, is HA minus HC divided by the sum of the hydraulic resistance for layer 1 plus the hydraulic resistance for layer 2. Or more simple still, we can write it as Q equals delta H, total change in hydraulic head across the column, divided by the sum of the hydraulic resistances. So in the end, this kind of hydraulic resistance formulation for Darcy's law is really easy to use. We just remember for layered soils, we calculate the total difference in hydraulic head from the top of the column here, point A, to the bottom, point C, and then we divide that by the sum of the hydraulic resistances, remembering that the hydraulic resistance is the length of the given soil layer divided by the hydraulic conductivity of that soil layer. So this is Darcy's law for layered soils, and it's convenient for working a variety of real-world problems.